All right, the next two questions, numbers 5 and 6, go right hand in hand with numbers 1 through 4, because these are asking us to identify whether the function has a maximum or minimum value. So that kind of goes along with graphing. Does it go up forever and it has a minimum, or does it go down forever and it has a maximum? And then to state what that max or min value is, and that comes from the vertex. So if we can find the vertex of these equations, like, we can do this pretty easily. So let's start off with number 5. Obviously, you have to know what form it's in. Is it standard form or is it transformation form? So this one you can see is in the ax squared plus bx plus c form. That's standard form. All right. Now, the leading coefficient, this a value right here, this is going to determine whether the parabola looks like this or looks like this. And that will determine whether it has a maximum or a minimum. So anytime the a value is negative, that means that the function is going to be moving downward on the left and right sides, which means it will have a maximum. And if the a value happened to be positive, then that means the function would go up on the left and right and it would have a minimum. So since our a value is -3, that means we look like this. That means it's a maximum. All right, now that we know that we have a maximum, we need to find it. So the only way to get the value is to find the vertex. Once again, we know that this is standard form. So if it's standard form, we've got to use that -b/2a stuff to help us find the vertex. All right, so let's see. The b value is 8, so that would be -8. The the a value is -3. So that would be over 2 times -3. That's going to be -8 over -6, which if you simplify that down, it's going to be 4/3. So our x value for our vertex is 4/3. That is not the max or min value, right? The max or min value is the y value that goes along with that x value. So we now need to plug that in and find out what the y value is that goes along with it. So going back to our equation, we've got -3 times 4/3 squared plus 8 times 4/3, and then plus 2. And this is a prime candidate for plugging into your calculator and just getting an answer. So if you type that all into your calculator, it's going to come out as 22/3, or your calculator might actually write it as 7 1/3, or 7.3 repeating. So that maximum value, that max value actually equals 7.3 repeating. All right, on number 6, you're doing the same thing, but this one you might notice is in transformation form. So we still have to decide whether it's a max or min, but then getting the vertex on this one is going to be a lot easier than the last one. So just like before, when you look at the number in front of x squared, you're going to look at this a value right here. You're going to look at this number at the very beginning and check to see if it's negative or positive. Once again, this a value is negative. That means the graph is going downward, which means it has a maximum. So both of these questions happen to be maximums. All right, now, to find the vertex in transformation form, you might remember that all you have to do is identify the h and the k value, and that's the vertex. So our h value right here looks like it's -7, but we know that it's the opposite of that, so it's 7. And then the k value is 15. So our vertex is going to be 7, 15. But what's the actual maximum value? Well, a max or a min value will always be the y values. So in this case, we just take the y value of that vertex. All right, so hopefully you can see the connection between number 5 and 6 and the graphing ones from the previous video. These questions are just asking you to identify what form they are and then basically find the vertex and identify whether it's a max or a min. All right, we're going to move, still in this video, we're going to move into the complex number section. So this was section 3.3, and most of what we do in section 3.3 is just working with imaginary numbers, working with complex numbers. All right, So this boils down to how well do you understand the world that is built on this little number I, right? So you might remember that I represents the square root of -1. So anytime we're doing the square root of a negative, I is going to be involved. Okay, so let's start off with number 7 here. We're going to simplify the square root of -121. So we can break up square roots into 2 parts by multiplication. So the easiest way to break this up would be to break up one square root, have one square root have the -1 in it, and have the other square root have the 121 in it. So then the square root of -1 can be written as I. The square root of 121 is actually just 11. So this whole thing can become just simply 11i. In question 8, it's very similar. We're going to break it up into 2 parts. One part to represent the square root of -1, and the other part to represent the 60. The difference here, of course, is that in the previous example, the 121 square rooted nicely just down to the number 11, but the square root of 60 does not square root down to just an integer number. So we actually have to simplify this square root. We have to think about 2 numbers that we could actually break 60 up into multiplied numbers, 2 factors, where one of those numbers could come out of the square root. And one of the easiest numbers to try is always the number 4. 4 is a single-digit number, so it's easy to divide by 4, but it's also a number that can come out of the square root. So 60 is actually divisible by 4. And 60 is 4 times 15. We have the square root of -1 at the front, and now we can evaluate each square root on its own. So the square root of 4 is going to become 2. The square root of -1 is going to be an I. And the square root of 15, that actually just stays the way it is, because you can't get an integer for the square root of 15. And even if you try to break up 15, it's just a 5 and a 3 anyway. So you don't have any pairs that you can take out of the square root. All right, moving on to number 9. Number 9 doesn't have any square roots showing in it. It just has the I a couple times. So this one's going to be a little bit easier. We can just actually multiply all 3 of these numbers together. The actual number part, the -3, the -7, and the 2, those 3 parts will just multiply together. So -3 times -7 is 21, and then 21 times 2 makes that part become 42. And then we also have to multiply all the i's together. So this I times this I times this I would give us I cubed. And you can't leave the I cubed as an I cubed, because you might remember in the imaginary number system, everything cycles back around, right? I equals the square root of -1, but I squared equals -1. I cubed actually just equals -I, and I to the 4th just equals 1. So since I cubed just equals -I, we're going to go ahead and change this I cubed to -I, so we can multiply 42 times -I, and that would give us the answer -42i. Remember, your answer will never have a power of I in it, because every power of I will break down into something like -1, -I, 1, or I. And we'll actually see that here in question number 10. If you raise I to the 22nd power, it literally means multiplying I 22 times, but we know it's just going to line up with one of these 4 numbers that we already know. So the way to find out what I to the 22 actually equals is to take the power 22 and divide it by 4 and figure out what the remainder is. So you might know that 4 goes into 22 5 times. 4 times 5 is 20, and that means that there's 2 left over. So since there's a remainder 2 here, that means that this I to the 22 is going to be the exact same thing as I to the 2. Whatever the remainder is, that's the power of I that it matches up with. So that means that I to the 22 is just going to be -1, just like I squared is -1. So that brings us to adding, subtracting, multiplying, and dividing imaginary numbers, complex numbers. So adding and subtracting is super simple. It's basically just putting like terms together. Remember that every complex number has a real part and an imaginary part. So all you got to do is put the real parts together. So we have a 10 and a 6 with a plus in between. So 10 plus 6 makes 16. And then put the imaginary parts together. So we have a -7i and a +9i with a plus in between. So -7 plus 9i would be +2i. So your answer there would just be 16 plus 2i. Here we have a subtraction. Nothing really changes. You just have to make sure that you subtract. So for instance, the real part 12 and the other real part 9, you just have to make sure that you subtract between. So 12 minus 9 is 3. And then for the imaginary parts, the same thing. We have a +5i and a -2i. And there is a subtraction between. So what that means is you're going to have 5i minus a -2i, which is actually 5i plus 2i. So that would give you +7i. So the answer there would be 3 plus 7i. Remember, every answer in this section will always work out to just be a real part and an imaginary part. All right, when we get to multiplication, numbers 13 and 14, you do have to do some foiling here. And, foiling isn't that hard. It takes a little bit of time, but it's a pretty quick process once you get used to it. So we're going to multiply 1 plus 2i times 1 minus 2i. We're going to start by multiplying 1 times 1, which makes 1. Then 1 times -2i. I shouldn't have put that plus there. So that would be minus 2i. Then we'll do the +2i times 1, which would be +2i, and the +2i times -2i. So +2 times -2 is -4, and I times I would be I squared. And then you got to simplify this, right? So you might notice that the two middle terms are like terms, but they actually cancel each other out. So those go away, leaving you with a 1 minus 4i squared. That's 1 minus 4, but then the I squared from earlier, we know that I squared is really just equal to -1. So that's like saying this -4 is multiplying by a -1. -4 times -1 is actually +4, +4. So this really comes out to just be 1 plus 4, which all simplifies down to the value of 5. That worked out nicely because these two are conjugates of each other. Because it's exactly the same real part and imaginary part, the only difference is that there's a plus in the middle of one and a minus in the middle of the other. That's actually always going to happen whenever you multiply conjugates together. And we'll see this come back into play in number 15 over here. But let's do number 14 first. So let's FOIL it out. 4 times 6 is 24. 4 times a -6i would be -24i. Then a -1 times a 6 would be a -6i. And a -1 times a -6i would be a +6i squared. This time the middle terms don't cancel out. So -24i minus 6i would be a -30i. We have that -24 from the beginning. And then, just like the last example, we're going to take this I squared and we're going to make it a -1. So that would actually make a +6 times a -1, which would be a -6. And once you put that down as a -6, you'll notice that the 24 and the -6 actually can combine. So 24 and -6 make 18, and then we just minus the 30i with that. Once again, a real part and an imaginary part is all that's left over. All right. So for this last one, this is going to be the hardest one because dividing with complex numbers takes a little bit of manipulation, a little bit of magic here, right? You can't just divide the number 10 or even the number negative 10 by a 1 plus 2i. Like, you can't separate it because denominators, they just don't separate that way. So what we need to do here is we actually need to multiply by the conjugate of the denominator. Because just like we saw in number 13, when you multiply two numbers times the conjugate, when you multiply one number times its conjugate, it actually simplifies down to just be a really nice number. It's just a number 5. All right. So to get this started, that negative that's sitting on the outside, I'm actually going to move that up into the top. So we're going to start off with a negative 10 over 1 plus 2i. That's okay to do because whenever a fraction is negative on the outside, it just means that either the top is negative or the bottom is negative, and you can choose. So since it's easier to move it up to the top, that's what I'm going to do. So then we're going to multiply by the conjugate of the denominator, which is 1 minus 2i. We have to multiply by 1 minus 2i on the top and the bottom because that fraction right here just equals 1. And that's really all you can multiply by. You don't want to change the fraction. So we can multiply by 1 and it will allow the purple fraction to stay the same. Okay. Now we've already done some of this work, all right? So we actually already did 1 plus 2i over times 1 minus 2i. That's what's going to happen down here at the bottom. 1 plus 2i times 1 minus 2i. So I'm not going to do it again. We already know that the answer comes out to be 5. All right. So I'm just going to go ahead and use our work from 13 to make this a little faster. Now, the top, on the other hand, though, still needs to be multiplied out. So that negative 10 is going to multiply by the 1 to become a negative 10. And it's going to multiply by the negative 2i to become a positive 20i. And that's kind of it. Once you're done doing that multiplication, and of course doing the FOIL multiplication on the bottom that we already did over here, this is the answer. But let me show you how to put it in a little bit nicer form. This you can actually break up into two parts. So you can say that the negative 10 on top is getting divided by the 5, and you can separate that from the 20i on top getting divided by the 5 as well. So what this does for you is it actually makes this a really nice answer. Negative 10 divided by negative 5 just works out to be a negative 2. 20 divided by 5 just works out to be a 4. And so once again, the answer we get is just a real plus an imaginary part. And that's how to divide complex numbers.